this video we will discuss more about or revise about the beta and gamma function. So let's start with the basic definition. We'll start with gamma functions. So gamma function, so for a positive value n, for a positive value n, that is n greater than 0, we define gamma n denoted by this capital gamma n as, we'll write down gamma of n. Sometimes we also write down like this, gamma of n, and it will be defined by integral 0 to infinity e to the power minus x to the power n minus 1 dx. So we will just discuss some properties, important properties of gamma function. Properties of gamma function. So the first basic property we have, gamma 1 is equal to 1. Then next one, gamma half. These are some values that we need to remember. And third one, gamma 1 by 4 into gamma 3 by 4 is pi root 2. Then the one more important property, because of which we called gamma function as generalized factorial function. So notice that in factorial we had n factorial is equal to n into n minus 1 factorial. So notice the similarity between these two values. So this is called generalized factorial function for gamma. We called gamma function as the generalized factorial function. Now using this property, we'll try to evaluate some values for gamma function. So let's start with some integer value. Let's say gamma of 4. So to evaluate gamma of 4, we'll write down that gamma 4 from this side as 3 plus gamma of 3 plus 1, that is 3 into gamma 3, which will be 3 into gamma of 2 plus 1, which will be 3 into 2 into gamma 2, which will be 3 into 2 into gamma of 1 plus 1, which will be 3 into 2 into 1 into gamma 1, but we already see gamma 1 is 1. So using that property we can say 3 into 2 into 1 into 1. So finally gamma 4 is 6. Similarly, we can evaluate gamma value at say 3 by 2. To evaluate this value, we'll write down 3 by 2 as 1 by 2 plus 1. So this will be half into gamma half, which will be 1 by 2 into root pi, because gamma of half is root pi. Okay, so in this way we can evaluate the gamma values in the positive side. So we will use the disguised formula. Remember, this was the formula that we used to evaluate our gamma values. So I will just rewrite this formula in this fashion. So gamma n is equal to gamma of n plus 1 divided by n, and this will be used to evaluate negative gamma values. So let's start with some example. So consider this example. We want to evaluate gamma of minus 3 by 2. So for this one, from above formula we are evaluating gamma n. So if n is equal to 3 by 2, n plus 1 will be minus 1 by 2. So this will be gamma of minus 3 by 2 plus 1 divided by again minus 3 by 2. So this can be written as gamma of minus half divided by minus 3 by 2. So now this gamma of 1 by 2 can be evaluated as minus 1 by 2 plus 1 divided by minus 1 by 2, and we will write down the 3 by 2 as it is, or minus 3 by 2 as it is. So we are having gamma of half divided by 3 by 2 into 1 by 2, which is 4 by 3 into root pi, as gamma of half is root pi. Okay, so this is how we will be evaluating the values. Now let's start with some integrals. We'll use our gamma function to evaluate most of the integrals. So let's start with this one. So consider this example where we want to evaluate I is equal to integral 0 to infinity x to the power 7 into e to the power minus 2 x raised to 4 dx. So note that first we will note that our gamma formula can be written down in this way, right? This is the value of gamma, and notice that the term that we want is e to the power minus x. So when we will try to get this term by substituting the values. So we will put e to the power minus 2x power 4 as e to the power minus t, so that the value of 2x power 4 will be t. So from this quantity we can evaluate the value of x as t by 2 to the power 1 by 4, and therefore we can evaluate the value of dx as we will evaluate dx as, or from here actually we can evaluate the value of this 8x cube dx is equal to dt, because here is power 7, so we can take out x cube common. From here also we can actually evaluate this as 1 upon 2 to the power 1 by 4 into again 1 by 4 into t to the power minus 3 by 4 dt, but this will be a little bit more complicated, so we will use this quantity. So again we will check the limits. So when x is 0, notice that t is also 0, and when x is going to infinity, that t is also going to infinity. From this formula it is clear. So we will again rewrite our integral I as integral 0 to infinity in terms of t. Notice that x power 7 can be written as x power 4, and we will write down this as, well, we will write down this first as integral in x, and now we will substitute the values. The limits will be same. Note that this quantity x power 4 can be written down as t by 2. This quantity is e to the power minus t. X cube dx, from this one we can write down that as 1 upon 8 dt. So this quantity we will take the constant outside. So 1 by 16 integral 0 to infinity e to the power minus t into t power 2 minus 1 dt. Why I am writing 2 minus 1 is because I want to compare with this quantity or this formula. So I can write down this as 1 upon 16 into gamma 2, but gamma 2 will be 1. So this integral I is equal to 1 by 16. Well, I forget to mention one thing. If n is a positive integer, then gamma n is n minus 1 factorial. We can use this direct fact to evaluate certain values. So let's start with the second example. So consider this one. Okay, this is not the example of gamma function. We will delete this one, and we will take an example from gamma function. So this one. So let's copy that example, and we will solve this example right now. So whenever you will see the log term in your integral, you will try to substitute this x term as e to the power minus t. So put e to the power minus t as x. Why we are only substituting x as e to the power minus t? Because note that x is having the positive limits. So since x will take the positive values, but log x may take negative values when x is less than 1 and greater than 0. So in this case x may take negative values, but exponential is always positive function, so that's why we are substituting x as e to the power minus t. So from this quantity we can evaluate dx as minus of e to the power minus t dt. We will take the log, so that we will have minus t is equal to log of x, and we'll check the limits. So when x is 0, that is log 0, it will go to minus infinity, and t is so t will go to minus infinity. This will imply t will go to positive infinity. And when x is 1, log of 1 is 0, so t is also 0. So therefore our integral I changes as integral infinity to 0. Notice that this is not integral 0 to infinity, but infinity to 0, so we need to add a negative sign in this integral. So let's this quantity will be e to the power minus t whole power m. This will be minus t power n, and dx can be substituted from this quantity as minus of e to the power minus t dt. So I will use this negative sign to interchange my limits. So I will have integral 0 to infinity e to the power minus mt into minus 1 power n into t to the power n, then e to the power minus t dt. We will take like terms at one side and take the constant outside the integral. So constant is minus 1 power n, integral 0 to infinity e to the power minus m plus 1 t into t to the power n dt. So again this is one formula which we have derived in the class, and I hope you guys remember. Integral 0 to infinity e to the power minus mx x to the power n minus 1 dx can be written down as 1 upon m to the power n into gamma n. So using this formula we can conclude our integral as minus 1 power n as it is. Here the role of m is played by m plus 1, so 1 upon m plus 1 power n plus 1, because value of n minus 1 is here n, so it will be n plus 1 for n, and this quantity will be gamma of n plus 1. So we can conclude this as our value. Now let's start the third equation or third example. So consider this example. So consider this example, we want to evaluate this quantity. So notice that the integral I can be rewritten as integral 0 to infinity x to the power m minus 1 into m minus 1 to the power minus x dx. Note that this quantity is some a to the power minus x, right? Where a is a constant. So we will just substitute that m minus 1 as a, so that our integral can be rewritten as integral 0 to infinity x to the power, notice that here is also a, so a to the power x dx. So where a is equal to m minus 1. So now to evaluate this quantity, notice that we have an exponential term, but we don't have the e power minus x function. Here it is e power minus x, and actually we want e to the power minus x. So the quantities that we can compare with this e to the power minus x is definitely this constant to the power minus x. So we will substitute a to the power minus x as e to the power minus t. By taking log, we will have minus x log a is equal to minus t, and therefore x is equal to t by log a. So therefore value of dx will be t upon or dt upon log a, because log a is a constant, and limits of the integration just a scaling by some log a value. So we'll definitely make sure that this a value is greater than 1, or log a value is greater than 0, so that we can take the log without changing the order of the integration. So we will have integral 0 to infinity. Note that in that case limits will be same, so check the limits for yourself. X to the power a, so in this case x can be written as t upon log a to the power a into e to the power minus t, and dx can be written as dt upon log a again. So we will take the constant outside the integral, so log a to the power a plus 1 into integral 0 to infinity t to the power a into e to the power minus t dt. So this quantity can be written down as integral log a to the power a plus 1 into this quantity. If we compare with our standard formula, we will get gamma of a plus 1, but we know a was m minus 1, so a plus 1 is m. So resubstituting the values, we will get this as I is equal to m minus 1 whole power m into gamma m. So we will stop the discussion about gamma function and we will start with the beta function from the next slide. So beta functions, so we will start with the beta functions. So the beta function for two positive values, say m and n, is defined as beta of mn is equal to integral 0 to 1 x to the power m minus 1 into 1 minus x to the power n minus 1 dx. So this is how we will define our beta function. So evaluation of beta function, that's the important point we need to remember. So evaluation of beta function. So to evaluate the beta function, let's say we want to evaluate beta mn, we'll use the gamma function. So gamma m into gamma n divided by gamma of n plus n. So this is how we will evaluate our beta function. So we will start with some example by evaluating beta function. Let's say we want to evaluate beta of say 4 and 5. So beta of 4 and 5 can be written as gamma 4 into gamma 5 divided by gamma of 4 plus 5, which is 3 factorial into 4 factorial divided by, this is gamma 9, so n factorial. Here we are using the fact that gamma n is n minus 1 factorial. So using this fact we could write down, use your calci to evaluate this answer. So this will be 6 upon 8 into 7 into 6 into 5. So 6 will get cancelled. So this will be 40 into 7, that is 180. So I can use the calci to evaluate such values. Again we will evaluate some beta of half comma, let's say 5 by 2. So to evaluate beta of 1 by 2 comma 5 by 2, we will use our formula beta m, gamma m into gamma n divided by gamma of m plus n, but 1 by 2 plus 5 by 2 is 3. So note that gamma of half was root pi, and this quantity can be written as 3 by 2 into 1 by 2 into root pi, and below we have gamma 3, which is 2 factorial. So this can be written as this 2 and this 2, so upon 8 this 3 and root pi into root pi as 3 pi. So this is how we will evaluate our beta function. We will evaluate a beta function at another value, in which we will use the third result that we have stated in the gamma function. So consider we are evaluating at say 3 by 4 comma 5 by 4. So to evaluate a beta value at this quantity, we have gamma of 3 by 4 into gamma of 5 by 4 divided by gamma of 8 by 4, that is 2. So this will be gamma of 3 by 4 into 1 by 4 into gamma of 1 by 4 divided by gamma 2. Notice that gamma 3 by 4 into gamma 1 by 4 is pi root 2. So this will be pi root 2 into this 1 by 4, and gamma 2 is 1. So you will have root 2 into pi divided by 4 as your beta 3 by 4 into 5 by 4. So using these beta functions, we will evaluate some integrals. So let's start with some integrals to evaluate beta values. So consider this example. So consider this example. Notice that again our beta function beta mn looks something like this: integral 0 to 1 x to the power 2 x to the power m minus 1 1 minus x to the power n minus 1 dx. Note that here is a 1 term and at this point there is a x term. So we need to change this 2 to 1. So to do that we will substitute this x as 2t, so that we can take 2 outside the integral as constant. So we will put x is equal to 2t, so that dx is 2 dt, and when we check the limits, when x is 0, definitely t is also 0, but when x is at 2, notice that t is at 1. So limits are automatically satisfied. So our integral I can be rewritten as integral 0 to 1. We are substituting 2t in place of x. So 2t square, 2 minus 2t whole power 13 and 2 dt. So when we try to evaluate this quantity, this is 2 square, then 2 power 13, so 2 power total 15, and this one is 16, so 2 power 16 into integral 0 to 1 t to the power 2 into 1 minus t to the power 13 dt. Comparing with our standard formula, we can write down this integral as 2 to the power 16 into beta of 3 comma 14. So this quantity we can evaluate this quantity using our calci. So notice that this will be 2 to the power 16 into gamma 3 divided into gamma 14 divided by gamma 17. If we put the values, this will be 2 factorial into 13 factorial divided by 16 factorial, out of which we can cancel out the 16 factorial and evaluate the value using our calci. So I hope you can complete this problem. Now we'll start with another example. Let's say this one. So copy. So consider this example. Notice again our standard beta function is given like this quantity. Beta mn is integral 0 to 1 x to the power m minus 1 1 minus x to the power n minus 1 dx. So we want to compare this like these quantities. So what we will do here, we will rewrite this integral as, I will take root 2y common, and this is multiplied by 1 minus 2y dy. Notice that we have something like 1 minus something here. So notice that again we can write down this as 2y power half into 1 minus 2y whole power half dy. So notice that we have something like 1 minus a function of y, and here is also a function of y. So to compare with this formula, we will again put 2y is equal to t. So we will get 2 dy is equal to dt, and when y is 0, t is also 0, but when y is half the upper limit, then t is 1. So using these substitutions, we can write down this integral I as integral 0 to 1 t to the power half into 1 minus t to the power half. Notice that dy will be dt by 2. So this quantity can be rewritten as integral 0 to 1 t to the power 3 by 2 minus 1 minus t to the power 3 by 2 minus 1 dt. And if we compare this with our standard beta function, this turns out to be beta of 3 by 2 comma 3 by 2. We'll evaluate this value as gamma 3 by 2 into gamma 3 by 2 divided by gamma 3. So 1 by 2 into 1 by 2 into root pi and whole square, because same value is repeated, and divided by 2 factorial. Again here I am using the fact that gamma n is equal to n minus 1 factorial if n is a natural number. So here I will have 1 by not 8, here 2 copies, 1 and this one, so there will be 16, 1 by 16 into pi, or pi by 16 I should write down, pi by 16. So we'll solve one more example and we will stop this discussion. Oh no, we are having 2 more examples before we stop. So let's start with the next example. So consider this example. Here before discussing this example, we will define beta functions in terms of trigonometric identities or trigonometric functions. So integral 0 to pi by 2 sine power p theta into cos power q theta d theta can be evaluated as beta of p plus 1 by 2 comma q plus 1 by 2. How this value comes? So we substitute in our standard beta function, because we can see a term like 1 minus x to the power n with the limits from 0 to 1 and limits 0 to 1. So we substitute x power n as sine square theta. If these limits were minus 1 to 1, then we have substituted x power n as cos 2 theta. Similarly, if we see the term 1 plus x to the power n and limits as say 0 to infinity, then we will substitute x to the power n as tan square theta. And if we see the limits 0 to 1, not 0 to 1 but 1 to infinity, in this case we will substitute x to the power n as 1 upon t. So these are some standard substitutions. And again there is one more thing, 1 plus x and 1 minus x comes simultaneously. Then we substitute x as again cos 2 theta. So here you can see 1 minus x to the power n is coming and the limits are 0 to 1. So we will go for the first substitution. So again rewrite the question, this one, and we will write down the substitutions. So we are substituting x to the power n as sine square theta, which will imply value of my x as sine power 2 to the power 2 by n theta. So dx will be 2 by n sine to the power 2. This will be 2 minus n by n theta d theta. So we will evaluate this value, or I should directly write down this as 2n minus 1. So that might be the better way. So we can write down our integral I as integral 0 to pi by 2 notice that limits will change from 0 to pi by 2. We will verify that claim. So if x is 0, notice that x is 0, so sine square is 0, so sine theta is 0, so theta is 0, and when x is 1, x sine square theta is 1, so theta is pi by 2. So our integral limits changes from 0 to pi by 2. Instead of dx, we are writing 2 by n sine to the power 2n minus 1 theta. I will write down d theta later. And notice that this is our cos square and power cos square theta and power minus 1 by n, because it is in the denominator. So comparing with our standard this standard formula in the trigonometric way or trigonometric functions, we can write down this integral. Well, we should not forget here half, so we can write down this as half into 2 by n beta of 2 by n by 2 comma this quantity is minus 2 by n plus 1 by 2. So if we simplify, we will get 1 by n beta of 1 by n comma this will be this 2 will get cancelled and here half will remain, so minus 1 by n plus half. I think I might have made a mistake. Let's check this answer once. If I remember correctly, this was some different answer, so let's see. So this one, okay, p plus 1 by 2, so this was our p plus 1 by 2. Okay, since notice that while evaluating value of d theta we made a mistake, so it should be cos theta d theta. So here it should be cos theta d theta, that is there will be a plus 1 power here, so that here will be plus 2 and finally we'll have plus 1 here. So value that we get is beta of 1 by n comma 1 minus 1 by n. So we'll start with our last example of this tutorial, I should say. So consider this example. So we want to evaluate 1 minus 1 to 1 plus x to the power p minus 1 into 1 minus x to the power q minus 1. So we from our these substitutions, if these two terms come simultaneously, we are substituting x is equal to cos 2 theta. So put x is equal to cos 2 theta. So this will imply 1 plus x, 1 plus cos 2 theta is 2 cos square theta, and 1 minus x, that is 1 minus 2 cos theta is 2 sin square theta. Notice that cos square theta minus sin square theta is given by cos 2 theta. So here if we add 1, we'll get the first result, and if we subtract 1, if we subtract this from 1, we'll get the second result. So we'll substitute the values. So when x is minus 1, then cos 2 theta is minus 1, that is 2 theta is pi. So this will imply theta is pi by 2. And when x is 1, cos 2 theta is 0, that is 2 theta is 0, cos 2 theta is 1 and q theta is 0, so theta is 0. So notice that, and also If we check the limit, if we check the value of dx, we'll have minus 2 sine theta sine 2 theta d theta. So substituting all these values in our integral I, will get integral pi by 2 to 0. This quantity can be written down as 2 cos square theta whole power p minus 1. This quantity as 2 sine square theta whole power q minus 1, and dx can be written as minus 2 sine 2 theta d theta, but sine 2 theta is 2 sine theta cos theta, and I will use this negative sign to interchange the role limits. So let's calculate values of 2 first. So 2 to the power p minus 1, 2 to the power q minus 1, so total are p plus q minus 2, this one plus 1, and from this expansion of this quantity we will have one more. So 2 to the power p plus q integral 0 to pi by 2 cos power 2p minus 1 theta cos sine power 2q minus 1 theta d theta. I am expanding this, and that's why 2q minus 2, and from this plus 1 is coming. So this quantity is 2 to the power p plus 1 beta of 2p minus 1 plus 1 by 2 and 2q minus 1 plus 1 by 2, and with a multiple of half. So this will be 2 to the power p plus q minus 1 into beta of p comma q. So we have solved one example from each type of the question paper or questions that may be asked in the beta and gamma function. We have skipped the special substitution chapter or special substitutions, because every substitution has different role. So go through them, and if you have any doubt you can definitely ask me. Thank you.